All right, so we've been working out examples together, and I want to work out some more. These are going to be a little bit more challenging. We're going to need to learn some tricks and some techniques to be able to solve these limits. So pay attention as we work through these because you'll need these tricks in your homework. So for the first one, I look at this and I say, okay, this is a rational function, but I can't just use the direct substitution property. Why not? Well, because this function is not defined at 0. You can't plug 0 in, otherwise you're dividing by 0. So things seem sort of hopeless, at least at first glance, but we're going to try anyway. So we're going to go ahead and see what happens if I simply expand out that quadratic. So let's try it. So this is going to be equal to the limit as h goes to 0 of what? H squared plus 4h plus 4 minus 4 all over h. And look what happens. I can cancel those 4's out. And so I get the limit as h goes to 0 of h squared plus 4h all over h. Now, you can cancel an h here, but I want to make sure that you see why. We're talking about h going to 0. It never is 0. It's getting closer and closer and closer to 0. So h in this fraction is never 0, and so I can cancel an h out. And so I'll come down here and I'll say, well, this is the same thing as the limit as h goes to 0 of h plus 4. And now we're going to let h go to 0. Remember, it never technically gets there, but it's getting closer and closer and closer. As h goes to 0, this is going to 0. And so you can see this is approaching, this is approaching 4. Another way to see this last step is this, at this point, you've reduced the limit to a polynomial function, and you can now use the direct substitution property, and you just get 4. So the first trick, just to summarize the trick, because you need to be able to do this yourself, the first trick is we expanded out the algebra, combined some terms, and canceled and simplified, and then things worked out. Okay, next trick. I don't know why I wrote no direct sub on the screen. I was going to tell it to you, but since I wrote it there, you can see it, right? You can't just plug in 0 because you're dividing by 0. And unfortunately, the trick that we just learned in the previous example doesn't work here. Why is that? It's the radical, right? So the radical kind of messes everything up. So I want you to think for a minute. What have you done with radicals in the past when you wanted to get rid of a radical? Pause the video if you want. Think about it. What are some ways that you've moved radicals around? You multiply by the conjugate. And so I'm going to multiply top and bottom by the conjugate of the top. The conjugate is the radical, so t squared plus 9. And it's the same term 3, but you just change the sign. If it was a minus, make it a plus. If it was a plus, make it a minus. Whatever you multiply by upstairs, you've got to multiply by downstairs as well. You can only multiply this thing by 1. And now if you want to FOIL it all out, you can, but the point is you don't have to. This is a difference of squares formula, and so this is the same thing as the limit. As t goes to 0, you're going to multiply this one times this one, and the radical goes away, so you just get a t squared plus 9. You're going to cancel inside and outside, and you're going to be left with minus 3 times 3, so you're going to get a minus 9. So t squared plus 9 minus 9 all over, multiply the bottom, t squared times a radical t squared plus 9 plus 3. So this part is just going right here times this part. Okay, well, you can see what to do next. Cancel those 9's out, and then actually, once you've canceled the 9's, we're going to cancel the t squareds as well. And so let's write this step by step, though, just so that you have good notes here. So you can write this as t squared over t squared times radical t squared plus 9 plus 3. I'll cancel those t squareds. This is the same thing as the limit as t goes to 0 of 1 over radical t squared plus 9 plus 3. Now at this point you can let t go to 0, and as it does, right, t is going to 0, so this is looking like root 9, which is 3 plus 3. So this thing is just 1 over 6. At this point, I'm just using the direct substitution property. All right, last tricky limit, and then we'll do something else. So for this one, I want to consider this limit. And this is an interesting limit. I mean, it's kind of strange. But if you think about it with me, sometimes when there's absolute values involved, it's worth considering the left-hand limit and the right-hand limit, particularly when you're looking at the limit as x goes to 0, because on the left of 0, you're always negative, and on the right of 0, you're always positive. And so I'm going to simply study the limit as x goes to 0 from the right of root x over x. And I need you to remember what it means. It means I'm going to 0. Here's 0. I'm going to 0. Oops. I'll draw it the other way. I'm going to 0 from the right. I'm coming from the right-hand side. And, well, if I'm on the right of 0, then x is positive, and that means absolute value of x is just x. And so this is equal to the limit as x goes to 0 from the right of just x over x, and that's just the limit as x goes to 0 from the right of 1, which you know is 1. Well, that wasn't so bad. What about from the left? Well, let's look at it. So we'll do the limit as x goes to 0 from the left of absolute value of x over x. Coming from the left, absolute value of x, think about what that is. It's important that we know that. It's just negative x. Think about it. X is negative, and so negative x is positive. So, for example, let's change colors so you can see it. If I want to do the absolute value of negative 2, I can say, well, that's just negative 2. Right, and that's what I'm doing down here. I know x is negative, so negative x I know is positive, and that gives me the absolute value. Well, now you can say, well, this is just the limit as x goes to 0 from the left of -1, which is just -1. And so what's the point? The point is, at this point, the limit does not exist. And if you want to abbreviate that, you can just say does not exist, D&E. And it doesn't exist because we learned that the full limit only exists if the limit from the left and the limit from the left and the limit from the right not only both exist, they both exist in this case, but they need to be equal, and they're not. You can see that. So let's break the video here. In the next video, we're going to look at limits and inequalities.